obviously you don't want to make a prediction for something that you've already solved in terms of a simulation, but instead deep learning surrogates, in contrast to most classical machine learning technologies, don't require a parameterized input. They don't need the features to be engineered by a human. We can reduce the amount of required simulations by 85%. Or how do I tell the model that I want to have a car that's looking like my brand design, but with the drag coefficient of a Tesla? Like literally. And the answer to that is it's not possible. We are still modeling physics.
Will AI replace engineers? What would your answer be to that? So in the past episodes, we've covered the potential of AI on other industries, but today we'll want to focus on one particular industry, which is engineering. And amidst this, what we call like technological renaissance, we have a special guest today, who is the founder of Navasto. But you're not doing like AI for like 1 or 2 years, but you've been doing it for over 10 years already. So Matthias, welcome to the show.
Thank you, Jousef. Thank you for having me. Looking forward.
Really, really exciting. Can you give the audience a little bit of background? Like, who is Matthias in the first place, and what is Navasto doing?
Sure. So my personal background is I'm an aerodynamicist. I'm an engineer. I studied aeronautics and astronautics here in Berlin, just around the corner, and then went on to do my PhD in aerodynamics. So I'm really someone who has worked with the problems that we're now solving for our customers. And after my PhD, I co-founded Navasto together with a colleague and friend who was coming from the automotive industry. And since then, we have grown to just a bit, about 20 people. We were based in Berlin with some additional offices here around in Germany. And what we're doing is, in essence, we are trying to industrialize artificial intelligence specifically for engineering applications.
That's super, super exciting. And we will talk about some of the case studies throughout the podcast. Probably the first question is going to be is, everyone wants to jump on this AI hype train right now, and especially engineers are a bit confused. What is possible? What is not possible? What, from your perspective, Matthias, do you think is possible nowadays with AI, with all the ChatGPT hype going on and whatnot?
Yeah. So first of all, it's super excited to see how the AI hype got started with ChatGPT. I mean, there was artificial intelligence or machine learning and deep learning around for many years now, but we have really seen a tremendous increase in interest in those solutions over the past month. And I mean, keep in mind that we are doing this for over a decade now. It's really super interesting to see how many people are now interested and trying to get started on that. So I think AI in engineering is something that's quite new to many people. And the underlying idea is nevertheless that you take data that's either project specific, meaning you have produced this data specifically to solve a problem, or it's just lying around in your data storages. So from older previous projects, so-called legacy data. And then you take this data and use it to train a machine learning or a deep learning model. And the underlying idea is then that after you have this model trained, you are able to make real-time predictions of simulation results based on this model. So instead of going through a simulation process, which is usually taking like hours or even days for DDS simulations in the automotive industry, what you get is a real-time answer for a new design that has obviously not seen by the model, but it's somehow related to what you have trained the model on. And this simply gives people the opportunity to real-time explore their design spaces and to change the way they are currently working in terms of development workflows. Because you now have the opportunity to simply parallelize the computation of the data and to take stuff that's already there, so it's not wasted on hard drives or something like that, but you can really take this data and put it to value, meaning that you have now this interactive, capable machine learning or deep learning model that is able to give you new results for something that's of interest at the moment you're working with it.
Yeah, super, super interesting. I think there was one misconception because you also post extensively, now starting to post extensively on LinkedIn. And there was one post in particular that went super viral. I think it got over 2,300 likes. And one comment always was, well, I already ran the simulation, so why would I need an AI prediction in the first place? What's your answer to that?
Yeah, I mean, like I said before, this technology is really new in the sense that a lot of people kind of have a misconception of what it's supposed to do. So obviously you don't want to make a prediction for something that you've already solved in terms of a simulation, but instead you try to get the answer to something that's maybe close to your training data. So in a standard development process, if you just change a small detail, but still want to check if it's valuable or a sensible change in your development process, you still need to run the simulation. And with AI, you now have the chance to really get the answer if this was a good or bad decision in real time back. So it only makes sense to query the AI model for a geometry or a parametric combination that was not part of the original training data, because for that you already have the answer.
Yeah, I think one thing that also is really mind-blowing, at least for me, is I know a little bit about AI, but I've talked to Jakob, one of your smart people at Navasto, and you also tackle the issue of trustworthiness in AI, which I think is super exciting. And there's something very simple for engineers, which is kind of a traffic light model, which is like you have a prediction made, and then it basically shows you if you can trust the model. So with a green light, yellow light, or with a red light. Can you maybe explain how that works? Because this is super exciting, I think.
I mean, the traffic light solution is something that we compute from the statistical properties of the training data or the model itself, so that the engineers don't have to actually deal with the underlying statistics or with complex model characteristics. At the end of the day, it's a best practice that's established by the method development department based on what they would like their engineers that are using the tool at the end of the day work with, or if the predictive quality is not sufficient for a new geometry, then they are required to go back and run the simulation. So in essence, what we are doing is in two aspects addressing the problem before a prediction is run and after prediction is run, or during the time that the prediction is made. First of all, we check if whatever new geometry is provided to the model, with what the model is queried, if that's close enough to the original training data. So what we do is we analyze the input geometry. We also analyze the boundary conditions of a new case that's supposed to be predicted, and see if there is something that's close enough within what the model has seen before, so that it is probable that the model can make a good prediction. So if this is not the case, so for example, if you have trained on a car and would like to predict an airplane, the answer is probably going to be, or most certainly is going to be, you cannot make this prediction. Now, once this model is good enough to make a prediction, what we then do is we run several forward passes through the model and get statistical properties on the predicted value. So for example, if you look at a drag coefficient, you don't just get one number of that, but you get a distribution of drag coefficients out of that. And then we can analyze this distribution of the predicted drag coefficient values and give the user feedback if what they get is trustworthy or not.
I think that sounds already like a huge step towards the kind of democratization of AI, especially for engineers or designers, right? Because
absolutely.
One follow-up question I might have is I've seen the Blender video that I've seen, like how you can basically change the geometry and tweak it a little bit, and you see kind of in real time how the surface field would change, or like the flow field and the wake, for example, of the car. Now the question is, what happens if someone misuses that? For example, they would kind of create a weird geometry of the spoiler. How can you go against that so that designers don't make weird choices?
Well, first of all, I think the Blender solution that we offer is a guiding tool for designers and stylists. So the idea there is that they really just get an idea in which direction they have to modify the geometry to reach a certain KPI. And if they leave the predictive scope of the model, they're going to get the feedback that the prediction accuracy is now not green, but for example, yellow. And at that point, they also know that they probably cannot trust the predicted drag coefficient or the predicted pressure fields, velocity fields, whatever is coming out of those predictions that they're currently looking at.
Got it. That makes sense. Obviously, in the huge field of AI, we've talked about deep learning. There's machine learning and then reinforcement learning and whatnot. In the beginning, or you mentioned deep learning. That also brings us to the so-called deep learning surrogates. Can you quickly explain maybe to the audience what are deep learning surrogates and what are the advantages, maybe disadvantages, also limitations?
Absolutely. So deep learning surrogates is something that have come up over the last some years. When we started a decade ago, there was no chance to really train a large enough deep learning surrogate simply because of the limitation of the hardware and also of some of the models. Deep learning surrogates, in contrast to most classical machine learning technologies, don't require a parameterized input. They don't need the features to be engineered by a human, but they learn not only the predictive part, but also to extract the features from a set of training data. So using deep learning surrogates, for example, you can directly learn on a geometry. So whatever comes out of your CAD program might be used to make a prediction for the drag, for the flow fields, for the surface fields, and so on. And in contrast, the machine learning models, which we actually have productive for many years now at different OEMs, require a form of feature set as input for the training. Usually parametric models, which also makes a lot of sense, to be honest. So deep learning surrogates is something that are being used a lot now, but there are industries, for example, the maritime industry, which more or less purely works on parametric input spaces. And in those cases, it absolutely makes sense to use standard machine learning techniques like a proper orthogonal decomposition or an isomap or something like that to make your predictions, because you pay for the feature extraction part of a deep learning surrogate with additional data. At the end of the day, the model doesn't only have to learn to make a prediction, correlating the input with a desired output, but also how the geometry is represented in some form of latent space. Yeah. So to put it short, in a parametric space where the features are already available, it's usually cheaper to do a standard machine learning technique. When this is not the case, for example, if you learn from a ton of different projects that were previously done, where there's no consistent parameterization, there it makes sense to use deep learning models.
Would you say if someone comes to Navasto and says, we have this kind of idea to jump on the AI hype train, let's call it like that for a second, what type of data can they work with?
Actually, what we usually need as an input, or what we see from our customers as an input, is previous CFD simulations, or FEA simulations, or whatever kind of problems they're trying to solve. So those simulations really contain all the information we need to train the model. They contain the geometry, they contain the boundary conditions, so that's a well-defined problem, and they also contain the solution files. So if there is someone out that has, I don't know, several hundred CFD simulations in their database, this is a very good starting point to train a model and to see how useful it is to work with a real-time model in the future.
I see.
Obviously limited to the predictive scope of what was in the training data.
Yeah, definitely. Would you say that once using or only using the training data, the physical properties or constraints are already included in the model, or how are they being taken care of these deep learning models, especially the physical constraints?
The physical constraints are simply a part of the input vector at some point. So you have the geometry, that's your input, and you also have, for example, an inflow velocity, or looking at something like a heat exchanger, the ambient temperature, or some kind of cooling fluid or something like that. So whatever is necessary to describe the physical problem for a simulation is also what we take as input to train a model and then to make the predictions afterwards.
Got it. Would you say that because CAE or some CAE tools have significant weaknesses, that AI acts kind of an enhancement for engineers in the current workflow? Or do you think AI will be the only solution in the future for engineers? Or do you think it's kind of more of like enhancement of the workflow, as I've already said?
Well, I think it's a productivity tool, which is very useful if there is the data to train a model, because it allows people to front load simulations. So you can run your physical simulations in parallel and then train a model, and then when you actually try to solve the problem, you get your answer back in real time. There's no way it's going to replace simulations, at least in the foreseeable future, simply because you need this well-defined, well-distributed, high-quality training database to train models on. And what we also very often see from our customers is that they really run the simulations. They need to train a model. So Audi is an excellent example here. because for them, we have built a workflow where the engineer on a Friday afternoon can simply define the design space they want to investigate during the next week. And then all the simulations required are run over the weekend. The model is computed, and then they work with the model during the next week, for example. So it's not going to replace simulations in any means. I think simulations going to be first principle based simulations going to be even more important in the future because those high quality data is needed. But I think what's going to happen is it's going to be decoupled. You're going to decouple the simulation you run from the current problem that you're trying to solve. And this is also something that we are seeing from our customers. The people that are working with the geometry work with the AI model, and in the background, simulations are spawned that improve the quality of the AI model if the algorithm finds that people are trying to investigate regions of the design space where a database might not be good enough already.
Got it. You also offer services in the terms of like upskilling engineers. How does that actually work? Because some of the engineers are obviously not data scientists. So how does it work from, let's say, an engineer has never touched an AI tool and then using Navasto?
Yeah. So this is something we have learned the hard way over the last decade. This technology is new to a lot of people, and therefore our approach is absolutely to not only teach how to use a tool, but also to teach how to use the new technology in itself. So what we are doing is once someone is interested in a solution, we go through them during an onboarding program from really explaining what potential use cases might be, listening to them, what use cases they might have in mind, then defining something that's realistically reachable within a certain time frame, and then going with them step by step to have this in place some months later, ideally productive at the people that are actually going to use it at the end of the day. Because I think the most important or the most problematic thing currently AI faces is that it's very often used in proof of concepts in research departments, but I think to be really useful, it needs to go to the engineers that are working with that possibility on a daily basis.
What are we talking about in terms of KPIs? Let's say time to market reduction or productivity increase. What are we talking about here in terms of like KPIs, main KPIs?
That absolutely depends on the customer, to be honest. So for a America's Cup team, we've demonstrated that we can reduce the amount of required simulations by 85%, which does not only come with money saved on HPC costs, but more importantly, on weeks saved before the entirety of the results comes back. Yeah. For others, we are talking about left shifting the availability of simulation data. An OEM who's working with us on a design tool, the Blender tool actually, where the designers that usually really only work on the shape get information on how their design choices might impact the KPIs. So it's very difficult to actually quantify there the benefit in terms of time saved, but the product's going to be improved because the initial output of those designers just going to be much more realistic to reach the overall KPIs. Yeah. And then, I mean, at the end of the day, if you think about a standard engineering process today, where people meet on a Monday, discuss the results they've obtained over the last week, and then they decide, okay, that's a good starting point. Now we need to continue to iterate. The time until they meet next time is probably something like some days or a week, because simply the simulation that they need to run to check if the decisions that were made are valid or not is that much. And if they're having a tool that allows them to judge their design decisions in real time, we're talking thirdly about cutting weeks or months of development processes.
Yeah, this is really, really crazy. When it comes to, I think a natural question then arises is, how do you actually use the tool? Is it done via an API? Do you have a no-code platform? How does it actually work?
Our tool is currently developed as an API because we have found that this is the most versatile way of fitting the customer workflows. Yeah. We see ourselves as an amendment to existing development workflows, meaning that the people want to keep their pre-processing in place because they have invested millions in developing that. And the engineers at the end of the day also want to see the results in the form they've already gotten it back over the last years, because at the end of the day, they don't really care if they get the result from an AI prediction or a simulation. So we need to fit our technology in between the pre-processing and the post-processing, and that's best done using an API which is versatile in terms of it can run on any operating system. It can be automated, because at the end of the day, you would also automate something like a CFD process. So we are really the same thing here, and we've decided to go with that. The model exploitation in itself is, however, done on the basis that the customer requires. So we have talked about the Blender plugin or the Blender front end. We have also integrated with ParaView, where rather the engineers than designers can interact with the models with a graphical user interface. And something that we've also very often encountered is that people simply want to use their standard post-processing pipeline. So for an engineer, not much changes, except for the fact that they get the results back much quicker in form of a PDF report or something like that. Or some of the customers want our software to send them an email when the results are back, so they get pictures in their inbox. So this is the way currently people interact with our solution.
Really, really cool. When we talk about the misconceptions of AI, because a lot of people think we just take a brute force approach like DeepMind or OpenAI, I think it's not going to work in engineering. So what do you think, what have you seen in the industry are some common misconceptions about AI, particularly for engineering applications?
One of them is probably the misconception that people think a huge amount of data is required to train a model. In practice, what a lot of OEMs are doing to really solve just one specific problem with an AI model requires something in the order of 20, 30, 50 simulations to be run. So that's one thing, the amount of data that's actually required. Also, one misconception is probably that it takes days or weeks to train such AI models, which is certainly true for a GPT-4 or something like that. But for engineering models, which are much more specific, we are talking about hours or days at max. But usually our aim is to train a model overnight. So that's one thing on the one end. On the other end, it's actually people think AI is magic, which is not the case. So I was talking to a lead designer at an OEM who asked me, okay, now we have trained some models with your software. Now, how do I tell the model that I want to have a car that's looking like my brand design, but with the drag coefficient of a Tesla? Like literally. And the answer to that is it's not possible. We are still modeling physics, and it's a magic. I think that's the other end of the spectrum that we're encountering. Yep. It's a productivity tool. It's not going to replace people. It's just much, much faster than going through a simulation.
Absolutely, yeah. When we again talk about the trustworthiness of AI models, because we have seen on LinkedIn how many comments actually telling you or supposedly saying, well, it doesn't work, it's just some fancy eye candy, whatever. How can we actually, or how do you assess the usability of a model in a practical environment?
Yeah, so there are some assumptions being made, because if you don't have solved for a specific geometry, you can never know for sure that the prediction is going to be accurate. You cannot, by the way, know for sure with a CFD simulation either, because that's still also a model. So there are two things I think that are necessary. The one thing is people need to get used to this type of technology. The more people start to use it, the better they're gonna be able to judge if a prediction can be true or not. So that's simply getting used to the solution, like CFD and also like the wind tunnel or something like that, and simply learning that this is one more tool in the toolbox, very quick, not magic. And the other thing is what I've talked before, checking if the new geometry, if the new setup is close to what the model has seen before. And then once you do a forward pass, you simply use the statistical properties of the model to find out if this solution can be viable or not.
Yeah. We've talked about some of the successes that you have had with OEMs and very renowned ones in the industry. What, from your perspective, definitely does not work when using deep learning models for, let's say, geometric data or like other types of data?
Well, throwing everything you have at the model and expecting to train one single model is something that we have at least not encountered so far as feasible. The data set needs to be kind of distributed equally in the parametric space. So it makes, for example, sense to train one model for limousines and one for SUVs. If you expect the model then to predict something that's completely out of those training data set clouds, then it's unlikely that the prediction is going to be very good, at least in terms of the scalar values. We found that making prediction for surface fields is actually much easier than predicting the scalar values.
I see. That's super interesting. I was wondering also in terms of like the AI skepticism. I mean, you talked about it being an enhancement tool, like a productivity tool as well. Like the common question is, will AI replace engineers? What would your answer be to that? Will it take some time? Will it happen at some point? Or is it just, it will never happen?
I think at the end of the day, AI is going to not replace engineers within decades, and probably then the engineers going to have a different job to do instead of being replaced. We are not even close to Jarvis, in my opinion. So I think the way of interacting with geometry is going to change. The way of interacting with problems is going to change, but not in the sense that anyone without any engineering expertise can solve those problems. You're still going to have some physical understand if what the prediction shows you can be plausible, can be true, decide what the next step might be to achieve something. There is always going to be compromises to be made. That's something that engineers need to do. So no, AI is not going to replace engineers in the foreseeable future. Hopefully they can develop better products more quickly. But Jarvis is still a large way out.
Otherwise, we engineers shot ourselves in the foot. But yeah, I also don't think it will happen in the next 25, 50 years. But let's see what's going to happen.
Well, I'm very, very careful with putting out those numbers since Bill Gates, I think.
Yeah, we'll see what's happening. I'm just going to put out a 50-year timeline and let's see. Maybe we'll have Jarvis by then. Who knows? I think people would also be super interested because you're like an expert in the field, obviously. How would you advise people to get started? Do you have any resources that you would recommend? Maybe specific lectures that you can watch online? Watch the webinars of Navasto, obviously. What else?
That's a very good starting point. Yeah, I get this question very often. And to be honest, there is, in my opinion, no great overview paper, something like that, that really covers the entire space. What I like to point people at is the YouTube videos of one of my former universities, the University of Washington. And I need to get back to you with the link if you're interested. But this guy really makes great videos on deep learning and machine learning for engineering applications.
Is it Steve? Steve Brunton? Not sure if he...
Sounds familiar.
Steve Brunton, probably Steve. He also was on the podcast. Yeah, I think he's the guy to... If you look for fluid mechanics and machine learning, he's the guy to look for.
It's also fun to watch.
100%, yeah, really cool videos. So I think we've covered everything so far. Is there anything that you would like to tell the audience, maybe Matthias, and what they should take care of, maybe if they want to delve into the field of AI? I mean, I know it's exciting, but maybe some recommendations from your end.
Well, I think a lot of people should simply just think about a good use case they might have, and that start to develop a strategy like they've done before with CFD and experiments and so on, and not be let's not say frightened about the fact that it's something new, but rather just take a quick peek into the possibilities and then start to think about what would be possible when results come back within milliseconds. Not really only looking about is a prediction able to reproduce a simulation result, but go one step further and think, okay, now just assume it's possible to get results back in real time. How would you change your workflow to get a better product out of that? How would that change the interaction between departments? How could it impact the exchange between designers, the structure guys, the aerodynamicists, and so on? How can actually multidisciplinary work look in practice if people can sit around a laptop and just try stuff out? So I think that's the message that I would like to pass on. Think about what could be possible, because what we are encountering very often is with every new customer we onboard, we find that they have a different use case. We don't know all the use cases.
Yeah.
It's super interesting for us also to learn what people can do with this technology and what they came up with ideas. And we're really just the guys that at the end of the day make the technology work, and are super interested to see what people can make out of that.
Definitely. You talked about use cases. Do you have kind of from all your experience that you've collected over the last years, what do you think makes a good use case in AI?
Well, let's give you just some examples. So what I've said before, the Blender implementation, which is our front end, but for the end user, the customer, it means a tool that can guide a designer. So it's really making knowledge available at a point in a process where today, with conventional processes, it's just not available. So that's one potential use case. One use case is certainly if you're aware of the fact that you're going to run 500 simulations or 1,000 simulations on a similar problem, like the America's Cup example I've just given, then it's absolutely sensible to take a look if maybe 100 simulations are enough to make the prediction for the remaining several hundred simulations, simply because it's going to save a lot of time. Then solving problem-specific tasks, like the optimization of a specific part of a vehicle, can be done with very small machine learning models. So something that really trains within an hour can be super helpful to have something in the next meeting to discuss with the other people what is a good solution from, for example, an aerodynamics standpoint, but can also be adjusted for requirements that are coming from other departments. And then at the end of the day, I think the coolest use case that we are seeing from our motorsports customers in Formula One is the idea of decoupling the work with the geometry and a problem from the simulations is certainly the most powerful use case that I've encountered so far. So knowing that a lot of people are working on a Formula One car with Blender against a machine learning model, a deep learning model, while in the background, the cluster is only used to make this model better, is really something where I see the future of engineering workflows to
Absolutely. That sounds super exciting. I was also more wondering in terms of like, let's say you have no idea where to start. Let's say you have a data lake, hopefully a data lake somewhere, and you have no idea if, should I reach out to Navasto? Maybe it's not even possible to start an AI use case yet. What are some of the indicators you would maybe tell to the audience, and maybe some people, maybe companies watching this podcast or listening to it? Well, we talked about data, obviously. We talked about the magic aspect. What else would you recommend to them if actually assessing if a use case is useful or not?
Yeah. So honestly, I think it's the easiest way is to talk to someone with the expertise. Navasto, for example, because we can figure out if it's sensible to go and build an AI model, usually very, very quickly. So if you're only running one simulation a day or something like that, then chances are pretty low that there's going to be sufficient data to train a model, or that it even makes sense to train a model, because apparently the process is already working very well with only one simulation a day. Apart from that, I think the people that are interested in really just accelerating their development work and are ready to try something new in terms of, let's not stick to experiments, let's not stick to simulations, but simply have a look what's possible and what not, I'm always happy to talk to them.
Perfect. And we'll put all the links that we've talked about and some email addresses and the link to your LinkedIn profile down in the description. Cool. I think we hit the 30-minute mark, kind of. I think it's the perfect time for the podcast. And the last words go to you, Matthias. Some last motivating word to the engineering fellow engineers out there.
Yeah, well, thank you very much, Jousef. So there was a lot said. Only a fraction of what can be said on AI and engineering has been covered. I think it's the coolest thing of my job is that I'm on this journey enabling people to use a new form of technology. And this is really what makes this job so interesting, and also the perspective so bright, because I think we really are currently at a moment in time where people don't only realize that the AI's potential, but dare to start using it. This is super interesting. Really, the fact that we are learning from our customers how use cases can look like is what's coolest.
Absolutely. Maybe I have to chime in here. Some people might not know it, but we also work on the marketing side of things for Navasto. You haven't been under the radar for a lot of people, but I think you have a huge potential. And I've only talked to a couple of your team members, and you're super smart people. And I think, yeah, you come up with a lot more use cases in the near future, and we'll talk about them maybe in the second part of this podcast series. So, Matthias, thank you very much, and super insightful. Thank you so much.
Sounds great. Thank you, Jousef, for having me.